Alright, let's continue. Okay, let me open the table of content first. Okay, we are still in, where is it? Chapter 28. Look here. The last time is that we are taking a look at this section 28.14 using quiz, sleeping instead of spinning. Now let's take a look at this section 28.15, different operating system, different support. Let me open that. Okay, 28 point, what is it, 15? Okay. Different operating system, different support. We have thus far seen one type of support. Excuse me. Okay, we have thus far seen one type of support that an operating system can provide in order to build a more efficient log in a thread library. Other operating systems provide similar support. The details vary. For example, Linux provides a full text. Oh, which is similar to the Solaris interface but provides more in-kernel functionality. I wonder what fulltext mean. I mean, mutex means mutual exclusion, right? So what fulltext in here means? Yeah, I'm still not sure. Okay, more in-kernel functionality. Specifically, its fulltext has associated with it a specific physical memory location as well as a pre-fulltext in kernel GUI. Okay. Callers can use fulltext call described below to sleep and wake as need be. Okay, Its fulltext has associated with it a specific physical memory location, as well as a pre-fulltext in kernel GUI. Caller can use fulltext call described below to sleep and wake as need be. Specifically, two calls are available. The call to fulltext wait. Okay, address and then expected. The argument for fulltext wait function or routine, I guess, puts the calling thread to sleep, assuming the value at the address is equal to expected. Okay. Put the calling thread to sleep, assuming the value at the address is equal to expected. If it is not equal, the call returns immediately. Okay, the call to the routine fulltext wake address wake one thread that is waiting on GUI. The usage of this call in a Linux mutex is shown in figure 28.10, page 19. Page 19, is this? Okay. 28.10. Okay. So put the thread to sleep if the address is equal to expected. Okay. If it is not equal, the call returns immediately. The call to the routine for text wakes one thread that is waiting on the queue. Okay. The usage of this call in a Linux smooth text is shown in figure 28.10. This code snippet from low-level log.h in the NPTL library, part of the GNU-libc library, okay, is interesting for a few reasons. First, it uses a single integer to track both whether the log is held or not. The height bit of the integer. The code snippet from low-level log.h in the NPTL library, okay, part of the GNU-libc or C library, okay, is interesting for a few reasons. Single integer to track both whether the log is held or not. The height bit of the integer and the number of letters on the log. All the other bits. Thus, if the log is negative, it is held because the height bit is set and that bit determines the sign of the integer. Okay. The number of letters on the log. All the other bits. Okay. Let me try understanding this. Single integer to track whether the log is held or not. Okay, the height bit of the integer. So we are using bitwise, I guess. Or maybe bit vector. I forgot what the name is. But basically we are using bit as an indicator. Maybe something like that. The number of letters on the log. All the other bits. Okay. Oh, so one bit to indicate whether the log is held or not, and the number of letters is the other bit. Maybe, let's say, we have something like this. Yeah, I'm trying to understand this part. If that is the case, right, maybe when the log is held, we take a look at this first bit, something like that, and then the rest is the waiters. What is the waiters again? Is it the, what is it called? The remaining thread in the queue. Maybe. Okay. Alright. Thus, if the log is negative, it is held. because the height bit is set and that bit determines the sign of the integer. Right? Maybe something like this. Hold, and then one waiter, and let's say if we have something like this, it means two waiter, question mark. I'm still not sure, but yeah, the height bit is to indicate whether the lock is held or not. The rest of the bit is the number of waiters on the lock. I'm assuming number of thread waiting for the lock, something like that. Okay. Second, the code snippets show how to optimize for the common case. Specifically when there is no contention for the lock with only one thread acquiring and releasing a lock. When there is no contention for the lock, okay. To optimize the common case. Specifically when there is no contention for the lock with only one thread acquiring and releasing a lock, very little work is done. The atomic bit test and set to lock and an atomic add to release the lock. See if you can puzzle through the rest of this real world lock to understand how it works. Do it and become a master of Linux locking. Or at least somebody will listen when a book tells you to do something. When a book tells you to do something, okay. Let me check this. Footnote, like buy a print copy of Offstep. Even though the book is available for free online, wouldn't you just love a hardcover for your text? Or better yet, 10 copies to share with friends and family, and maybe one extra copy to throw at an enemy. One extra copy to throw at an enemy. The book is heavy, and thus chunking it is surprisingly effective. Yeah, imagine throwing the book with hardcover to someone. Yeah, that's gonna hurt, I assume. Okay, let me take a look at figure 28.10 here. This one, figure 28.10, Linux-based Futek logs. Okay, Mutex log. Okay, we have Mutex here. Was clear. P31 was clear. We got the Mutex, Fastpad, atomic bit test set. Okay. Alright. Atomic increment. Oh, okay. If atomic bit test set. Okay. 31. P31 was clear. Oh, I assume 31 with what is it? Can decimal to binary, I guess, binary digit. Maybe this one. Okay. 31. Oh. Is this the one? that means it is clear. Maybe. Okay. Bit set. Atomic. Okay. Mutex. Atomic decrement. Oh. Okay. Mutex. Have to wait first to make sure view text value we are monitoring is negative or log. Okay. Text. Wait. Mutex unlock. Okay, I think this to counter result in 0 if and only if there are not other interested threads. Atomic, okay. There are other threads waiting for this mutex. Wait, one of them. Okay. There are not other interested thread. To counter result in 0 if and only if there are not other interested thread. So maybe what this means is that if there are no waiters or the thread waiting for the log, this will turn to 0. But then if this is turned into 0, then we won't return, but make this mutex. Okay, there are other threads waiting for this mutex. Make one of them to counter. Oh, wait, what? If and only if there are not others interested thread. So if there is no waiters, the thread that is waiting for the log, is this gonna turn into 0? But if not other interested thread, then what are we waking up? I mean, I assume this will turn into 1 if there are no waiters, so that we immediately return, right? Let me check again. Where is it? When there is no contention for the log, with only one thread acquiring and releasing a log, very little work is done. The atomic bit test and set to log and okay. So yeah, what I understand from this one is that maybe if there are no waiters, the thread that waiting for the log, we will return immediately. But if there are any thread waiting for the log or mutex, maybe we wake one of them up. Maybe something like that. So I'm not sure about this comment. Yeah. Maybe I'm not understanding this comment correctly. Okay. Let's continue. Okay. Okay, we have this mutex log, atomic increment. So we increment the mutex number, be something like that. So if it is, what is it called? If it is log, if the, what is it called? If the mutex is log, we immediately return, maybe something like that. Oh, wait a minute. Equal 0. And this is the, what is it? The bits or binary digit. If it is equal 0, okay, we got the mutex, increment mutex, okay, bit test set. Come to the routine, okay. Let me think. Put the calling thread to sleep, assuming the value at the address equal to expected. Equal to expected. Bit test set. The high bit, check whether the lock is held or not. So maybe this atomic bit test set, check whether the, what is it called? This high bit is locked or not. Maybe something like that. But yeah, what kind of operation is this? We got the mutex. So maybe if it is locked, right, we immediately return. Is that it? If it is unlocked, we increment the, what is it called? The mutex. And then check again whether the mutex is locked or not. Have to wait first to make sure mutex value we are monitoring is negative. Okay. We are monitoring is negative. If it is still not negative, we continue the iteration. If it is negative, maybe we wait. Something like that. Okay, so maybe this one is checking if the if the lock held or not. If it is held, we return immediately. If it is not, we increment the atomic mutex here, and then doing some spinning again, I guess, and monitoring if the mutex changed to, or the futex, I guess, in this case, the futex changed to negative. And then if it is negative, we wait. Okay. What is V? Is V the expected address? Maybe. So maybe V in this case is the expected address. Okay. Yeah, I'm kind of curious about futex. What is futex? Oh, is there any main page? Fast user space locking. Oh, okay. Look like there is a main page. Oh, okay. Let me check here. Futex system call provide a method for waiting until a certain condition become true. Fast user space locking. Oh. Okay. The futex system call only when it is likely that the program has. When the program has to block for a longer time until the condition becomes true. Other futex operation can be used to wake any process or thread waiting for a particular condition. Okay. For a longer time until the condition becomes true. Okay. Waiting until a certain condition becomes true as blocking construct in the context of set memory synchronization. Okay. When using futex, the majority of the synchronization operations are performed in user space. Oh, okay. Alright. That's then how it works. Yeah, this is getting more confusing. Okay. But what I assume is that if, what is it called? If the lock is held, we return immediately. But if the lock is not held, the, what is it called? The hike bit, this one, the hike bit from 31 decimal, I guess, decimal number is 0, or I mean maybe the mutex address and the bit 31 result in 0. Yeah, basically the hike bit here is 0, or maybe positive in the sign to complement here. Then we continue to this one, increase incremental mutex, and then check again if the lock has been held or not. If it is held, we decrement the mutex and return. If it is, what is it called? If it is not held, we are waiting until the mutex locks. Till the mutex lock, and then we wait. Oh, wait a minute. Then what about this one? If we are monitoring in this case. Wait a minute. Puts the calling thread to sleep is equal to expected. Oh, wait a minute. Does that mean this check if another thread get the lock? Is that it? And then let's say if another thread didn't hold the lock, we check if, what is it called? If the current thread hold the lock or not. Maybe something like that. And then if the current thread holding the lock, we wait. Yeah, I'm not sure about this condition. Like, why we decrement the mutex when, let's say, when it is unlocked. Oh, wait a minute. So this is probably true when the lock is held, I guess. Yeah, I'm not sure about this one. Atomic bit test set. Okay. Mutex 31. Yeah, if this one return 0, right? What does it mean? If this is returning 0, does that mean the lock is held? Or not? Right? Whether the lock is held or not. And assuming to this one, if it is negative, then it is locked. P31 was clear. We got the mutex. Yeah, I'm still not sure about this one. Atomic bit test set. What is the result of this? Like, what is it called? If we return 0, what is the meaning of that? Is it locked or unlocked? Assuming from this, maybe if this one return 0, it means that we got the lock, maybe, or the lock is held. The lock is held by this mutex. Maybe something like that. So we got the mutex and then return immediately. Yeah, I'm still not sure about this one. And why, if this condition is true, we decrement the mutex? I mean, if it is unlocked, right? Why are we returning? Yeah, so my assumption is that this will return true if the lock is held, so that when the lock is not held, we increment the mutex, test again whether the lock is held or not. If the lock is held, we decrement the mutex and then return. But then what is this for? Mutex wait. We are monitoring. Okay, mutex value we are monitoring is negative. Yeah, if we are monitoring if the mutex value negative, then what this condition check? I'm getting confused. Okay. Yeah, what this condition check? If we are monitoring the mutex value in this one, I guess, whether it is locked or not, and I assume if it is negative or locked, we are waiting until this mutex is unlocked, maybe something like that. Push the calling thread to sleep, assuming the value at the address is equal to expected. Assuming the value at the address is equal to expected. Yeah, the only possibility that I can think of is that we check whether the lock is held by the current mutex, maybe. If it is held by the current mutex, we immediately return. That's why there's this comment. We got the mutex for the current thread. And then let's say if the current thread did not get the mutex, we increment the mutex, and then check again if the current thread get the mutex. Okay, what is it called? Mutex log. Check if the current thread had the mutex, and then current thread had the mutex, return immediately. Okay, if not, increment the mutex. Okay, maybe something like this. Increment the mutex. Spinning. Check if the current thread had the mutex or not. Okay, if the current thread had the mutex, decrement the mutex and return immediately. If not, check whether other thread had the log. The thread, or maybe another, I guess. Another thread hold the log or the mutex, or yeah, I'm not sure if the mutex here is the same as the log, you know. Okay, maybe the current mutex had the log. Yeah, maybe the mutex is the thread. Let me check. Yeah, I'm still not sure. Is mutex in here the same as the log here? Generic mutex. Let's take a look at this. Showing that only one person may use the bedroom at a time. Okay, so maybe mutex is the log, I assume. when I'm having a big heated lesson at work, I use rubber chicken, okay, which I keep in my desk for just such occasion. If you don't hold the chicken, you cannot speak. You can only indicate that you want the chicken and wait until you get it before you speak. Okay. You can hand the chicken back to the moderator. Okay. So maybe Mutek is the lock. The chicken is the Mutex. People holding the chicken are competing threats. Due to unlock request. Okay, so maybe let's add some information here. Mutek is the lock. Check whether another thread holding the mutex If not, check whether another thread hold or held the mutex. If it is, but then address is equal to expected. Address is equal as expected. So maybe inside this mutex is, what is it called? Is the address for the thread, maybe? If it is, put the current thread to sleep. The current thread held the mutex. Okay. If mutex is the lock, right? Are we checking if the mutex is locked or not? Okay, we got the mutex. Yeah, from this comment, I assume the current thread got the mutex, so we return immediately. If the current thread did not hold the mutex or the lock, we increment the mutex and then check again. If the current thread held the mutex, but then we wait this one. I'm still not sure. Check if the current thread held the mutex or not. If the current thread held the mutex, so does this mean maybe maybe this one check if the current mutex, it's if the current thread held the mutex. Again, if it is held the mutex, we decrement the mutex value from the queue, maybe something like that. And if it is not, we check whether the mutex held by another thread, which means the value become negative. If not, we keep trying, checking this again. Check if the mutex held by the current thread or not. And if it is negative or locked, or the mutex held by another thread, we put the current thread to sleep. Maybe something like that. To sleep. Okay. If not, we keep checking if the current thread held the mutex. Not. Back to the top of spinning. If it is, put the current thread to sleep. Maybe something like that. Maybe. And for this one, mutex unlocked. Okay. Mutex is the lock, I guess. If there are no other threads waiting for the lock, we immediately return there are other threads waiting for the lock. We wake up the other thread. We wake up one of these threads. Maybe something like that. Yeah, it's getting more confusing. Okay, to face lock. Okay, let's take a break first. Oh, there's a lot of people here. Okay. Yeah, if you can see this, right? When I'm on focus mode, I rarely check the chat, Now I'm on break mode, so I'm looking at the chat. What is going on in the chat? Okay. Alright. Okay, oh. Headshots. Atomic beta set could be read in this case as Mutek is trying to take the mutex. Oh, is trying to take the mutex. Whether the mutex is taken or not is stored in the 31st bit. Oh, okay. Attempt to set the 31st bit to 1 and return the previous value. If the previous value was 0, then it succeeds and set the bit to 1. Okay. Mutex try take is trying to take the mutex. Whether the mutex is taken or not is stored in the 31st bit. Okay. If atomic beta set succeed and set the bit to 1, that means that the current thread now owns the mutex. Oh. Okay, wait a minute. Wait, not that one. Okay. If atomic beta set succeed and set the bit to 1, that means that the current thread now owns the mutex. I'm kind of curious. Wait a minute. Set this bit, I guess. Right? Head store. If atomic beta set succeed and set the bit to 1, that means that the current thread now owns the mutex. Okay. That held the mutex or not. Okay. If not doing this, wait, let me add some explanation here. Because yeah, It's kind of confusing, at least for me. Okay, mutex. If it failed because the bit was already 1, then that means another thread already has the mutex. And so the current thread steps, and so the current thread sleep by calling footex wait. Okay. So this atomic bit test set trying to take the, what is it called? Trying to take the mutex, I guess. The mutex for current thread and save that in P31. I guess this one, I assume. Or maybe this one. And if it is 0, and if it is becoming 0, yeah, which binary number do we use? Is it the 2 complement here or this one? I'm assuming this one, right? Okay. I agree that this code is confusing when you are trying to understand mutex and footex. It uses some non-obvious behavior of those complement integer to pack those state values into 32-bit. Oh. It uses some non-obvious behavior of two complement integer to pack those state values into 32-bit. The top bit stores whether the mutex is taken or not, and the rest of the bit indicate how many threads are waiting to take the mutex. Since the top bit is used as the lock or unlock state, when the mutex is taken, top bit is 1, the mutex value as a whole is negative. Okay, so maybe we can try this. I'm not sure if Python will show this. What is it? 31. Okay, something like this maybe. Oh, is this 32? Wait, let me check. Or maybe 31, but yeah, it's different. Okay. Hello Asra, welcome. How come you have zero distraction? I'm focusing, I guess. Yeah, I'm not sure how to answer that question. I mean, I'm interested in learning operating system, right? So I'm logged in or something like that. You want 32 bits with the leftmost bit set to 32 bits. So wait, not that one. So I guess maybe something like this. Not the number 31 in binary. Okay, 32 bits. Alright, no, not this one. Okay, that means we probably using something like this, I assume. Wait, let me put this here, I guess. So if, what is it called? If the leftmost speed or the height speed is 0, that means the move tag is not taken. Oh, that one. Okay. Okay. It looks like, yeah, this is not the correct binary digit. Okay, right. So this one, this is 32-bit. 32-bit, right? Wait. Oh, you know what? Let me try to copy this from the chat. Okay, 32-bit. Oh. Alright, so what is it called? If the height bit is 1, right, the move tag is taken, and if it is become 0, right, save that in bit 31 in the leftmost bit 31, and if it is become 0, or maybe something like this, right? Wait a minute. Oh, so it won't change it to 0. Okay. Oh, it won't change it to 0. Wait, so does that mean if the height bit is already 1, it won't change it to 0? So does that mean if, what is it called? If we save that in the, oh. Wait a minute. Let me think. Trying to take the mood text for current thread. So what? If the height bit is already 1, it won't change to 0. So does that mean if that's the case, how do we change the condition? It won't change that to 0. Or maybe compare that. And what it us try to take the mode text by setting the top bit to 1. Oh, take the mode text by setting the top bit to 1, and if it is 1, okay. Current thread by, have you covered atomic operation yet? In this book, only briefly, not full, I guess. Yeah, we briefly talk about atomic in this section, but not going deep. So probably not yet. Yeah, if I remember correctly, the one that this book explains is that atomic is either all or nothing, something like that. So other than that, yeah, maybe not yet. Maybe we will cover that in the future. I'm not really sure. Definition, okay. Maybe in this one. Yeah, I'm not really sure yet. Do you have any, reference maybe for atomic operation? Atomic bit set use some special CPU instruction that simultaneously check if the value in memory is not the expected value. Okay, that simultaneously check the value in memory and set that value only if the value in memory is expected value. Otherwise, if the value in memory is not the expected value, it does nothing. Okay. Some special CPU instruction that simultaneously check the value in memory and set that value only if the value in memory is the expected value. And set that value if only the value in memory is the expected value. So does that mean, what is it called? The 31 bit in here is the expected value, maybe something like that. So we set the top bit to 1 if the value is not the expected value. The expected value is 0 because this is a set operation. Is the bit you are checking. Okay, by setting the top bit to 1, current thread by the top bit to 1, right? The top bit to 1. So maybe we start out from 0, something like that. Again, I'm not sure if my analogy is correct or not. So we start from bit 0, something like this, I guess, and then set the top bit to 1, which make it 30 bit 31, maybe. Okay, and check if it is true or not. Maybe something like that. The one is the bit you are checking. Check if the result is equal to bit 31. Question mark. Maybe something like this. So we start from bit 0 here and then set the top bit to 1, right? Which in this case make it the, what is it called? The binary digit, something like this. And check if the result is equal to this bit. Is equal to this bit or bit 31. Maybe something like that. Okay, correct me if I'm wrong. Trying to take the mutex for the current thread by setting the top bit to 1. That's correct so far, but you're missing the case for if the top bit is already 1. Oh. Okay. If the top bit is already 1, and I assume the bit is from this mutex value, I guess. Is that it? If that's the case, then if the bits you are looking at are the bits from the mutex variable. Oh, okay. If the mutex bit let me put in another paragraph. If the mutex bit already have the top bit set to 1, we do nothing, and if the mutex bit is or have the top bit or have the top bit 0, we set the top bit to 1 and check if the result is equal to what is it called? Bit 31. Maybe something like that. And if the MUTEX bit have the top bit 0, right? Something like this maybe. We set the top bit to 1 and check if the result is equal to bit 31. Okay. Then yeah, why is this comment calling bit 31 was clear? I am not sure. So maybe this is the full explanation. If the MUTEX bit already have the top bit set to 1 with do nothing, and if the MUTEX bit have the top bit 0, something like this, we set the top bit to 1 and check if the result is equal to bit 31. Okay, that's pretty close, but the check occurs before the set occurs. The function returns the previous value of the top bit. Oh, the check occurs. So if the function returns 0, that indicates it set the top bit successfully. If the function returns 1, it did not set the top bit. Maybe something like that. The function returns the previous value. Oh, the function returns the previous value of the top bit. The comment is saying that if we take the if branch and return on line 5, then bit 31 was clear and we succeed in taking the MUTEX log. If we take the if branch and return on line 5, this one, then bit 31 was clear and was succeed and we succeed in taking the MUTEX log. Oh, okay. Let me try understanding this. The function returns the previous value of the top bit. The function returns the previous value of the top bit. Okay. So maybe check if the top bit or maybe leftmost bit is 0 or 1, right? And that if it is 0, we set the top bit to 1. If the and then if the top bit is 0. Okay. If the top bit is 1, we do nothing. Oh, is it similar to, what is it called? Maybe compare and swap. Where is it? Maybe this one, compare and swap. So we return the original or the previous value. It's basically a compare and swap operation on a single bit. Oh, okay. Yeah, that is kind of confusing for me. Okay, on a single bit, we do nothing, and finally, with the limitation that it can swap in an arbitrary value. It can only swap in a one specifically. Alright. Yeah, because we didn't provide this. Okay. So, wait, and finally we return the original value. So maybe if we, let's say, if we make some pseudocode, I guess, from the previous, what is it called again? Atomic bit test set. And then let's say this is mutex, and what is it? Expected, maybe something like that. So this is the original mutex, and then we check if, what is it called? Original equal expected, and then we set the, what is it called? The mutex, or maybe something like this. The, what is it called? Hey, wait a minute. If it is not expected, I guess, right? If it is not expected, let's say the original is 0 and the expected is maybe 31, or maybe something like that. We change this to, what is it? Expected. I'm not sure if this is correct. Okay. And then we return the original. Yeah, how do we simulate the bitwise here? You're on the track, keep going. Okay, yeah, it's getting confusing. And thank you for the help. Okay, if not equal expected, yeah, how do we represent the bitwise check here? we gonna use the, like, what is it called? The masking, maybe something like that. We are masking the original bit with the expected bit. Yeah, maybe something like this. Let's say, what is it called? The original have something like this. Yeah, something like this. And then the expected have something like this. You know what? Let's try using this instead. Okay, and then the result is 0, I guess. Wait, let me check. Programming bitwise operation. Okay. Maybe check in this one. Oh, not and okay. Yeah. This is what I mean. Bitwise operation. Okay, right. If what is it? 0 and 1, we get 0, and if 1 and 1, we get 1. So maybe we need to do something like this. The negation. This is the original result, and negation result is 1. Maybe something like this. If that is the case, what is it called? We change the bit, I guess. Like maybe using the bitwise OR to change the bit, like for example this one, 0 or 1 becoming 1. So maybe I'm not sure if this is correct. Yeah, maybe something like this. Okay, the expected is 0. Oh, remember we need to succeed and set if the top bit is 0. That's what we are looking for. Oh, the expected is 0. Okay, wait. And if the expected is 0, is this the expected result or the expected from the parameter here. The expected is 0. We need to succeed and set if the top bit is 0. Oh, does not take expected as an argument. Oh. Is which bit to check? Oh. So the second argument here, or parameter I guess, is, what is it called? Is bit is set bit, maybe something like that. Expected is hard code to 0. Okay, there's a spirit function atomic bit that's clear, which tries to set the bit to 0 instead of 1. Bit or bit index. Oh, bit index. Okay. And then there is this expected, right, is 0. Okay, so the expected is 0, and let's say if the original is 0, okay, the negation result is also, the negation result is 1, original, okay, and then n bitwise expected, and then this one may be bit index. So we have OR operation for the mutex bit with the bit index, maybe something like that. Wait a minute. Negation result. If true, change the top bit from 0 to 1. Okay. If not, right, let's say the original is 1, expected is 0, the result is wait a minute, is this correct? Maybe not. Maybe we use the ortho or bitwise operation here. Maybe. So maybe something like this. It become 1. The negation result is 0, right? And then this will become false, something like that. Maybe. Okay, if it is 0, the OR will turn 0. Okay, negation result will turn 1, and then we change. Maybe something like this. from 0 to 1. Okay. Close. You want something like left shift bit index to shift the 1 to the correct position. Oh, okay. Then you can use that as a max with the bitwise and operation to retrieve that bit from the mutex variable. Okay. Oh, right. Okay. To shift the 1 to the correct position. Right. Okay, so previously we have something like this, right? So if we do left shift, it will become something like this, I assume. Yeah, 32. Or yeah, 32. And then 1. And then we change this. Okay, so maybe do we need to shift that in variable? Maybe we can do something like this with index to get the, what is it called? The top bit, right? Wait, let me put this in variable, I guess. I think, or maybe not. Yeah, from what I understand, maybe something like this. Not 0. One to left shift the number 1. Not the mutex variable. Oh, only this one. Not the mutex variable. Okay, does that mean we are doing something like this? We left shift, right? We have moved shift number 1, not the mutex variable. Can that to max with the bitwise and operation to retrieve that bit. The if condition is incorrect. Oh, wait a minute. The if condition is incorrect. Let me try. The if condition is incorrect. So does that mean what is it? Are we also left shift this one? Oh no, I don't think. Wait, maybe. to left shift this two to get the leftmost or the top bit, and then this one so that we get this expected. Mutex. Or maybe let me think. Channel left bit index expected. I mean, let's say or maybe we left shift from this. I'm not sure if this is correct. Yeah, and we have this original, right? Let me think. I mean, if the one that is incorrect is this one, the OR. Yeah, let's say the original have bit 011 or something like that. So maybe something like this, but then is this correct? We are changing the bit from the mutex. Wait. Are we not dereference the mutex? Yeah, basically only get this one, right? The top bit, I guess. Or maybe using XOR. Oh, wait a minute. Maybe using XOR, exclusive OR, but then again, I mean, if the expected is still 0, right? That didn't really change that much, I assume. Okay, that's not correct. F shifting mutex will shift the top bit out of the register. F shifting mutex will shift the top bit of the register. Out of the register. Oh, wait a minute. Does that mean we need to write shift? Left mod bit. If you left shift, it will shift that bit of. Oh, right. For example, yeah, something like this, I guess. Something like this. If we left shift, right? Let's say 1, 2, 3, 4. 1, 2, 3, 4, 5. Let's say if we left shift 5, maybe it will become something like other than 5, 4. Something like this. So this will disappear, I guess, something like that. If I remember correctly. Like this one. Okay, so that's not correct. And maybe do we need to left shift? I mean right shift. Maybe something like this. So that, let's say we have something like this, right? Left shift by, what is it called? Right shift, I mean. 1, 2, 3, 4. Okay. It will become something like this, I guess. The bit you want is in the leftmost bit. Okay. And we left shift this bit 1 because wait a minute. If we left shift this too, let's find that out. Okay, not that one. Let's check the binary here. Okay. Okay, interesting. I assume, wait a minute, 32, I guess, for the left shift, right? This is the 32 bit from 1, right? And when we left shift 31, it becomes something like this. Okay. Right, I forgot about that. Okay. And now let's, what is it called? Let's say we have the address, positive address, maybe 69, something like that, like this, and then maybe right shift. Okay, it becomes 0. But what we want is this one, right? Or this one. Okay, wait. If I use negative, I don't think Python will show negative here. complement binary. The complement in Python. I want the representation. Python presentation of the complement binary. Can we do that? Oh, using pin? If we provide a max, okay. Maybe we should provide a max there. Maybe something like that. But when is this? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Equal bits. What is this? Let me try. One multiplied by bits. Okay. Maybe the correct one is this one. Maybe. And then like this. I assume this is 31. Is this correct? I'm not sure. Wait, not that one. Okay. Oh. Getting Python to print those complement correctly is weird. Yeah. I mean, I'm just curious, I guess, how to represent this. Okay, something like this. Oh, how many F is there? 3. Maybe I can copy this. Wait. No. One, 2, 3, 4, 5, 6, 7, 8. Okay. Alright, maybe something like that. And then we do the right shift, right? If I understand correctly. 31. Oh, okay. Alright. So we get this top or left bit. Oh, the redshift goes inside the negative one. Okay. This one. Yeah, this is the, what is it called? The marks, right? Okay, my bad. Okay. And bit cast the negative number into an unsigned integer. Bit cast the negative number into an unsigned integer. Okay. But then is this correct? The representation for, what is it called? For the original here. Let's say the, what is it called? The value in mutex is negative. Maybe something like that. And then we write shift. Remember, negative into complement is that a binary digit. So you're basically reshifting 131 times. Okay. Yeah, we are shifting the bit 31 times from this 32. Okay. You're actually running into a kind of stupid denial of redshifting sign integers. Since the leftmost bit represents the sign, you have two options when redshifting. Since the leftmost bit represents the sign, you have two options when redshifting. Arithmetic redshifting, what Python is doing, will shift replicate the leftmost bit. Oh, so if the number was negative, the leftmost bit is 1. Additional 1 will be shifted in from the left. Oh, okay, so that's why we didn't really get what is it, the right binary digit, maybe something like that. Yeah, the total of redshifting sign integer, right? The logical redshift will always shift 0 in from the left, regardless of what the leftmost bit was. She helpfully just throw up its hand and calls it undefined behavior if you use redshift on assigned integer. Oh, okay. Right. Okay. Oh, so that is the detail for the Python implementation. Maybe something like that. Redshift can only be used on unsigned integer in C. Okay. Only unsigned integer in C. Okay, so does that mean, what is it called? The value in mutex here must be unsigned. Is that it? The standard anyway. Specific compiler make do their own thing. Right, it is undefined, so anything can happen at that point. Okay, wait a minute. Let's take a look at this code again, right? So is this correct or not if you're doing redshifting? I mean, the mutex here can be negative, right? So if doing redshifting can lead to undefined behavior, maybe we should not do this. That's undefined behavior since you are redshifting assigned integer, right? That's what I'm worried about, so maybe not like that. And maybe we need to use max, something like that, like using this max for 5, 6, 7, 8. Maybe. Let me try. Or maybe let's try 10. Okay, we got this. Okay, and wait a minute. Maybe after using the masking, we need to clear the rest of the bit. Maybe something like that. Wait, is the masking correct though? Okay, then what about 10? Okay, maybe. Remember, in your pattern you are printing a binary representation of decimal number 10. Oh, right. Wait. Okay. So that is, yeah, that might be incorrect. Okay, this is getting tricky. Okay, maybe something like this. we add some, what is it called? We add maybe I should use this. Still the same, okay. We add max. I'm not sure if this is correct, I guess. Let's say, what is it called? We have 111 here, and then max. I use -1 decimal can, right? Okay. But is this correct? The representation. Yeah, maybe. And then we have this one. Yeah, let's maybe something like this. Okay, and then this will become 1, right? Okay. After this, should we use the if we use the right shift on this one, it is undefined. Or maybe wait a minute. Maybe, I mean, if the original is 1, right? The original bit is 1, the expected is 0. If we use n as the max, if we use n as the max, then it will become 0 to you basically have two options if you are trying to extract the leftmost bit. Do you want to keep trying to work out it yourself, or would you prefer I list them? You're pretty close. Yeah, that's the challenge, right? When we are so close, it's getting harder. Let me think first. Okay. We have two options. Trying to extract the leftmost bit. Now I wonder, do we extract the leftmost bit during this one, during when we get the original value here? or during this condition. I assume we will need to extract the the leftmost bit during this original, right? Because we are returning the original in the function here. Again, to check with this, I guess. For the record, this is why I didn't much care for the code example in the PDF you were reading. It includes a bunch of nuanced bit operation, and that just distract from the threading code. Oh, okay. Yeah, I mean, again, I'm also a newbie, right? So I didn't know whether I should take a look at the code or not. So by default, I usually take a look at the code and trying to understand what it means. And like you said, sometimes it is confusing, right? For example, like this one, what this function do, something like that. But yeah, I usually take a look at the code just to try to understand and see maybe if there is something that I feel not correct or something like that. I'm trying to, analyze the example. So I'm trying to analyze the example and see if I can understand that or not. A part of learning process, I guess. Something like that. So let me try this. But yeah, like you said, headstone, maybe it is distracting to the threading code. You should definitely be familiar with the bit operation you are working with if you are doing this type of low-level code too. So it's not a waste of time, right? That's why I'm trying to get familiar with this bitwise operation. Yeah, one step at a time, Okay. Okay, if that is the case, right? Maybe if I, maybe I can. Oh, wait a minute. Did I need to do something like this? So using the bit index as the max, maybe. And then, I mean, if the bit index is something like this, right? We only interested in this one, the leftmost bit, and then ignore the rest, right? But then, how do we... how do we specify? Hint. If bit index is 5, so you are trying to set the 5th bit, the representation of bit index would be Okay. To set the fifth bit, the binary representation of bit index would be that one. Okay. Oh. To set the fifth bit. If the representation, okay. Okay. So to set the fifth bit, meaning if you do between masking or selecting the lower bits of mutex. Oh, okay. If you do between masking or selecting the lower bit of mutex. Yeah, because okay, the representation something like that. So maybe should we do something like this? Maybe wait. So what is it called? We left shift 1 with the bit index, right? So that we can get, what is it called? Something like this, the binary representation of this, and we get this one. So we remove the rest of the, what is it called? The rest of the bits, something like that. But then how do we, what is it called? Oh, wait a minute. If let's say, I'm not sure if Python will show this. Okay. Oh, is this correct? I'm not sure. Okay. So if let's say the result is 0, right? We get something like this. And if the result is 1, oh, wait a minute. Or maybe yeah, let me think. It is 0, 0, 0, right? Oh, okay. So maybe we have the other binary here and then just using this OR bitwise operation. And then negation that. I mean, I'm not sure if we need to, what is it, right shift? Maybe we need to right shift too. Oh, here in original. Okay, line is correct. Okay. Now maybe the problem is this one. I'm still not sure what is the problem here. I mean, do we need to, what is it called? Do we need to right shift this one? That will max all the lower bits, leaving only the leftmost bit in the original variable. Okay. And that make me wonder, do we need to right shift something like this so that it will become maybe something like this? Yeah, we max the lower bit. Think about it like this. If the leftmost bit is 0, what will the numeric value of original be? And if the leftmost bit is 1, what will the numeric value of original be? Okay. Yeah, if the leftmost bit is 0, I think the numeric or the decimal value would be something like this. I assume is 0, and if the leftmost bit is 1, right, we probably have something like this, the numeric value or the binary value. I mean, I'm not sure what the decimal will be. Let me check. Swap. Okay. Yeah, maybe this one, right? The decimal number. And if we change that to this one, become 1. So given that, what should you write in your if statement to check if the leftmost bit was 0? Oh, okay, in the, what is it called? In the condition, right? In the if statement. So maybe we can do something like this, right? What is it? Or, and then after that, wait a minute. need to change this one, the if statement, or do we need this original one? I mean, if the original something like this. Oh, wait a minute. But yeah, isn't this gonna be undefined if we are doing this? I mean, again, the say sign to complement thing like this. Oh, okay. If I write shift in this one, we cannot get the negative value to return, right? So we need to write shift maybe in this one, and then check that with the expected. Is this something like this? Is it something like this? Original right shift bit index. Remember, expected is a constant here, so you don't need an actual variable for it. If you don't want one, so you're right shifting assign integer again, right? That's what that's what my concern. Okay, so we cannot do this because it is undefined. So to change this, okay, let me, I guess, put in here to change this to, what is it called, to this, right? Maybe we need to max again, or maybe XOR, something like that, so that this one becomes 0 again according to, where is it? Maybe this one, bitwise XOR, right? 1 and then 1 become 0, and then 1 and 0 become 1. So maybe we need to max that. See, it's annoying for this. You don't actually need to write shift to do what you are trying to do. Okay. Yeah, I'm trying to understand how we can do this option. You can do what you are trying to do with the right shift, or you can cast your mutex pointer to unsign in to bypass the entire problem. I'm trying to avoid casting. Right. So yeah, let's try with the first option, with the right shift. I'm not sure if this is correct. Wait a minute. Let me try this. Oh, okay. What is the hex number for this? Maybe we can use the hex number. Maybe. Okay. Is Python gonna show that? I'm curious. Okay. So maybe we can use XOR, something like this. That rightmost one in the text number should be 0. Oh, it should be 0. Oh, that rightmost one, something like this. Should be 0. Wait. Rightmost, right? I mean, if it needs to be 0. You're kind of going down to wrong track again. Yeah, I mean, I don't even know where the track is, you know. So I just keep going. Okay. I mean, isn't this like, think about it like this. Statement check whether the condition is 0 or not 0, which is what you have in the original value anyway. The condition is 0 or not 0. It is what you have in the original variable anyway. Okay. So if this is 0, right? I mean, it needs to be either 0 or not 0, I guess, or 1 in this case. If I understand correctly. The condition is 0 and not or not 0. Right? Oh, the two possible value the original value can have at this point. Two possible value. Okay, at this point, it is either, if I understand correctly, it is either this one, right? Or maybe using decimal. Okay, right, it is either this one or this one, because we already, what is it called, clear up the rest of the bit, so we only take the leftmost bit here. Okay, and then right, and then the, what what is it called? This variable here, right? What is it called? And then this constant here is 0, right? It means having this one. Okay, something like this maybe. So if we are using, okay, let's say we have negative number in the mutex, and then we need to check whether this one is what is it called? Yeah, this is original, this is constant, something like that. So I'm thinking of making this one turn into something like this. I'm not sure if this is the correct way, but I'm trying to make the original something like this into this one. The easiest way is to have right shift, right, casting this into unsigned, and then what is it, right shift, something like that. You're overthinking it. Okay. Okay. Yeah, I'm confused. Wait a minute. I mean, we don't need to make it like this. Is that it? But then, if you don't make it like that, oh, okay. Then what is the if statement? Yeah, I'm kind of stuck. Okay. Original here. If we didn't use or in here, wait, are we gonna use this? Bitwise not or negation, or maybe complement, I guess. value you're looking for is 0. You don't need to change original to compare it again with 0. The value that I'm looking for is 0. We don't need to change original to compare it again with 0. But I want to confirm first, is my understanding of the, what is it called, the value of the original, something like this, correct or not? I mean, if my understanding of the current value of original is incorrect, then yeah, maybe I need to reevaluate from there. Okay, that's correct. That's what it will be if mutex had the top bit set. Okay. So we don't need to change this, but we need to check whether the result is 0 or not. Okay, that the result is 0 or not. Are we gonna is 0 or not? If we are performing bitwise node, okay, let's say I'm still overthinking it. Okay. Okay. So we might not need this bitwise operation. Yeah, let me think. Oh, wait a minute. Is it something like this? But no further bitwise operations are necessary. Take a step back and remember what the if statement is actually trying to check for. Yeah, that's correct. Okay, yeah. I just realized that if statement is check for 0 or non-zero, right? Okay. Okay, yeah. That if statement check 0 or non-zero. If the original is 0, right, like this one, right, the negation would be, what is it called? Would be 1 or non-zero, right? But if this is like this, I'm not sure if the negation will be 0 though. Yeah, whether 0 or not, but the point is that we need to check whether it is 0 or not. So we need to check this one, the priority here. Other than this, it's true, I guess. Oh, I mean false. Other than this, it is false because of the negation. Okay. Nice work. It took me a long time to realize this. Okay. The function as a whole is correct conceptually. There's some silly C and different behavior you have to work around. To actually implement it, there will be in all compilers, but the core of it is correct. Also, the real implementation used the log cmpx.ghg instruction on x86-64. Other CPUs have their own instruction for the same thing. Okay. To lock the memory cache and prevent other threads from interfering during the operation. Okay. cmpx.ghg is Intel specific or install speed. I assume install, what is it called? Intel syntax, maybe something like that, for compare exchange. Okay. Yeah, okay, it's Intel language. Intel is kind of known for having terrible naming. Well, at least they are trying, you know. That's what important. Okay. Yeah, what is it? cmpx.ghg for compare exchange. Man, if I ask how long have you been programming? In C programming language, probably less than a year, I guess. So I'm quite new in the C programming language and this bitwise operation. That's why I'm not really good at it yet and get confused about this bitwise operation. So there is that. I have some, what is it called? Some experience in, let's say, Golang or something like that. But I rarely use this bitwise operation in this programming language. So yeah, I learned something new. At least. Okay. And I'm kind of curious. Are we, what is it called in this case, right? Mutex. What is it called? Bitwise OR here. Are we changing the address in mutex? You're doing well. Most people wouldn't be at atomic operation at this point. I mean, I'm curious, you know, so that's why I'm going into this rabbit hole, maybe something like that. Yeah, but it is confusing, let's put it that way, about this atomic or multi-thread application, right? And that's what I'm looking for. I'm looking for a challenge. Yeah, to make things hard. Something like that. Okay. Yeah, I need to understand about atomic stuff. You read about needing to dereference MUTEC for the XOR assign operation. Okay, so we need to dereference this, I assume. Right? Okay. And then we return to original value here. Okay. Alright. That's quite a bit of information. Okay, but well, I'm having fun, I guess. And thank you for the explanation. Heads drawn. Okay. Alright. Okay. Maybe let's continue this on the next session. Yeah, I need to. What is it called? I need to absorb. Is that the word? I need to absorb what's going on. Yeah, just understanding this is quite a bit of a challenge. And again, maybe the example is just confusing. I'm not really sure. So for text weight here. Okay. Okay. Do you stream often? Yes, I'm trying to live stream every day, but the time is inconsistent, you could say. I do live stream every time I can, you could say. There's what is it called? Discord. If you want to join the Discord server, I usually announce that in the Discord when I will be live streaming. The Discord link is in the channel description in case anyone wants to take a look. Okay, so yeah, let's continue this on the next session. Either we're taking a look at this again, or maybe moving on to this one. Yeah, maybe moving on into this one, and I will update the notes in my what is it called, GitHub repo, in case anyone wondering. This is what my notes or experiment about this book. Let me copy this in the chat, or you can take a look at the description. There are some resources there. Yeah, this is the previous note, like this one for example. Oh, there's no notes in here. Just some experiment using the thread. I think this one, yeah, there is some info here. I will be putting the note for the chapter 28 after we finish this. What is it called? After we finish this chapter. So let's continue this on the next session. Thank you for watching and see you next time. Bye bye.